The research focuses on applying machine learning in education, particularly in analyzing educational big data to evaluate student academic performance. With the increasing popularity of the Internet in education, a vast amount of educational data is being generated, making effective utilization crucial in educational data mining. A machine learning model based on long short-term memory networks, LSTMs, is employed for an in-depth analysis of educational big data. LSTMs are useful for processing time series data, enabling the capture of time-dependent and long-term trends in students' learning activities. This approach benefits analyzing student progress, engagement, and behavioral patterns, ultimately supporting personalized education. The effectiveness of the deep learning method in predicting student performance is verified through an experimental analysis, comparing the performance of different models using strict cross-validation techniques. The research falls within the realm of machine learning methodologies, focusing on neural networks, and explores key concepts such as education big data, performance analysis, machine learning, and LSTMs. Educational big data encompasses vast amounts of information generated by students' daily learning and life activities, including academic affairs, financial systems, library systems, and other sources. Analyzing this data enables predictions about student behavior and potential risks, laying the foundation for personalized educational services. Higher education students often face challenges such as weak self-control, lack of motivation, and internet addiction, which can lead to increased psychological stress and self-harm behavior. To address these issues, schools and authorities must strengthen supervision, intervene in inappropriate behavior, and provide counseling for students with psychological problems. Educational data mining is crucial for analyzing and predicting students' academic performance. By applying machine learning and deep learning techniques to student data, early intervention can be provided for underperforming students, improving their academic performance and overall school life. Behavior patterns and lifestyle habits can be analyzed using big data, revealing correlations with academic performance. Daily behavior patterns and good online habits are positively correlated with academic performance, while social media activity is closely related to students' mental health. Effective use of big data in education can identify students at risk of academic underperformance and take targeted measures to improve their performance and mental health. Educational data mining aims to extract useful higher-order features from raw data and use actual data records for analysis, including information on students' courses and families to predict future performance and potential. Evaluating students' academic performance is a critical component of the educational process, enabling educators to understand students' learning needs and develop more effective instructional strategies. By leveraging existing student information, it is possible to predict future performance, reduce failure rates, and optimize academic outcomes. Research has primarily focused on using existing data to predict students' grades in each semester and identify those at risk of failing courses. A study by Aya et al. Demonstrated the effectiveness of deep neural networks in predicting student academic performance, achieving an accuracy rate of 89%. Similarly, Hyungjun et al. Utilized students' location information to analyze their activity tracks and identify a correlation between students' trajectories and their average GPAs. Predicting students' grades at the beginning of the semester has been a long-standing topic in education big data research. Through education data mining, analyzing the correlation between students' data can effectively assist educational institutions in daily management and target support for at-risk students. Sadiq Hussain et al. Applied deep learning regression models and linear regression models to educational datasets, solving the overfitting problem by adjusting parameters and finding that deep neural network models outperformed linear regression models in mining and predicting students' academic performance. Shahab Bo et al. Proposed a standard and intuitive classification method to describe the level of students' academic performance using a hidden Markov model, constructing a compact learning performance trajectory to explore the association between learning performance trajectory and academic success. Furthermore, Javier Bravo Agapito et al. Constructed a series of models to predict early student achievement using Moodle interaction data and performance characteristics from 802 undergraduate students, identifying 4 factors that had the greatest impact on student achievement: the number of visits to forums and glossaries, questionnaires, assignments, and the number of submitted assignments. The paper explores the relationship between smartphone use and student achievement, emphasizing the significance of healthy usage habits and self-regulation. It also delves into the integration of education big data with long short-term memory, LSTM, models to forecast student performance. The authors detail the expansion of the basic LSTM architecture to handle intricate patterns and dependencies in education data. This involves the forgetting gate, which determines what information to discard from the cell state, calculated using equation 1. The model can also incorporate non-time series features through extended input gates, enhancing prediction accuracy. The paper concludes by discussing multitask learning scenarios, where LSTM can predict multiple outputs simultaneously, such as student achievement and engagement. The paper discusses the dynamic adjustment of the LSTM model in response to changes in the educational environment, such as the start of a new semester or changes in course content. This is achieved by modifying the learning rate of the model or directly adjusting the model parameter W, based on the following update rules. The learning rate, which controls the step size at which the parameter is updated, can be adjusted using strategies like exponential decay. This approach helps the model adapt to changes in students' behavior patterns and maintain its performance over long runs, especially when dealing with non-static data sources. It is critical for education policymakers who need to respond based on the most up-to-date data. The experimental setup leverages the EDNet KT1 dataset, a large-scale education dataset designed for knowledge tracking, which integrates data on the interaction of millions of students on online learning platforms. This dataset provides detailed records of student activity, including clickstream, time of answers, correctness of answers, and more, making it suitable for in-depth research on personalized learning, learning path optimization, and other areas related to educational technology. The goal of the experiment is to utilize the long short-term memory, LSTM, model to track and predict student learning performance. The experiment involves data pre-processing, including data cleaning and feature selection, and the selection of key features such as correctness of answers and timestamps. The LSTM model is configured with 128 cells, and a dropout rate of 0.5 is employed to reduce overfitting. The Atom optimizer is used for training, with an initial learning rate set to 0.001, a batch size of 32 or 64, and a total training period of 50. Performance evaluation is performed through metrics such as accuracy, precision, recall, and F1 score, while k-fold cross-validation is used to ensure the reliability of the results. The accuracy metric represents the proportion of the total number of samples that the model predicts correctly. The F1 score, a blended average of precision and recall, provides a balanced reflection of the model's performance, particularly important for unbalanced datasets. Figures 1 and 2 display the students' performance prediction results, comparing the accuracy and F1 scores of different methods, respectively. These results demonstrate the effectiveness of the LSTM model in tracking and predicting student learning performance, showcasing its potential in personalized learning and learning path optimization. The evaluation of the model's generalization ability is conducted using k-fold cross-validation. This technique divides the dataset into k subsets, training the model on K1 subsets and testing on the remaining subset. The process is repeated k times, each time using a different subset as the test set. The final result is usually the average of the k evaluation results. This method reduces the variation of model evaluation results caused by different data division methods, making model evaluation more stable and reliable. The results are presented in Figure 3, comparing F1 scores across methods using k-fold cross-validation. This approach is crucial for ensuring the robustness of the model's performance in real-world scenarios. The paper underscores the transformative potential of educational technology solutions in enhancing student learning outcomes through personalized learning and performance optimization. It emphasizes the critical role of big data and machine learning techniques in education to improve the quality and effectiveness of education. The study also identifies areas that necessitate further exploration in future research, including algorithm optimization, data privacy protection, and the integration of multimodal learning environments. Experimental results demonstrate that advanced machine learning models, such as the proposed model, generally provide higher accuracy and F1 scores, especially in the case of k-fold cross-validation, where these models demonstrate superior stability and reliability. The application of different teaching methods and settings, such as traditional instruction, online learning platforms, and blended learning models, in data-driven decision support systems underscores the great potential of edtech solutions for personalized learning and student performance optimization. The paper provides a comprehensive review of related works, including studies on educational data mining, student performance analysis, big data analytics, and the utilization of ensemble techniques for prediction of academic performance. These findings underscore the significance of leveraging machine learning and big data in education to enhance the quality and effectiveness of education, as well as identify areas requiring further investigation in future studies.